Dear students, starting with the introduction to differentiability, first of all, a recap from class 11 standard. We had defined the derivative of a real function as follows. Suppose f is a real function and c is a point in its domain. The derivative of f at c is defined as you know this one, limit h tends to c, f of c plus h minus f of c upon h, isn't it? We know this one, and provided this limit exists, this is very important. Except this existence, you can't say the function is derivable at the point x is equal to c, and it is denoted by f dash c. You know this one, ddx of f of x at the point x is equal to c. The function is defined as f dash of x is equal to limit h tends to 0 of f of x plus h minus f of x upon h. This is the first principle of derivative, known as first principle of derivative. You know this one, we discussed in 11th standard, and the notations are as usual, y dash dy dx or ddx of fx, like this. Okay, also the phrase used here, differentiate f of x with respect to x, that means f dash x. Okay, now we discuss mathematically also by graphical method. Differentiability at a point. Okay, let us consider that fx be a real valued function. Fx be a, write it here, fx be a real valued function, a real valued function in its domain, say ab. Okay, open interval ab, and consider that a point b c which is belonging to this open interval a comma b. Okay, then f of x is said to be differentiable at the point x is equal to c if and only if limit x tends to c f of x minus f of c divided by x minus c exists finitely. This is very important, exists finitely. Okay, this exists finitely. And what is this? Actually, this one is nothing but your f dash c, f dash of c, the derivative of f of x at the point x is equal to c, isn't it? Now f of x is differentiable at x is equal to c. That means this exists finitely. This one exists finitely. Now what does it actually indicate? It indicates that limit x tends to c minus of f of x minus f of c upon x minus c is equal to limit x tends to c positive of f of x minus f of c upon x minus c, isn't it? X minus c. That is, left hand limit and right hand limit are equal because this limit exists finitely, isn't it? So you can now substitute on the left side. You may consider that x is equal to c minus h, so that what will happen, this is a limit according to class 11 standard rule, h tends to 0 f of c minus h, isn't it? F of c minus h minus f of c upon this is x minus c, so it will be of only minus h. Yes, we have to show it this one actually, otherwise you can't understand it. Say x is equal to c minus h when x tends to c minus, this minus is nothing but the directional sign. Actually x is proceeding to c from the left side of c. Okay, so then when x tends to c, then obviously this h tends to 0. H tends to 0. For this we have written here h tends to 0. And what will be x minus c? Obviously from this one, x minus c is equal to minus h. For this in denominator I have written minus h. Similarly, if you substitute on right side also, you will get limit h tends to 0, because on the right side you have to consider x is equal to c plus h, and then this after substitution you will get here f of c plus h, minus f of c upon x minus c, and it will be h, isn't it? So now on the left side you are getting limit h tends to c, h tends to 0, f of c minus h minus f of c upon minus h, this one is known as the left hand derivative. Okay, this is known as left hand derivative, in short LHD, left hand derivative, at x is equal to c, and the right side is known as the RHD, a right hand derivative, at x is equal to c. And in short, you may also write this one as L f dash c. Okay, left hand derivative of f of x at the point x is equal to c, and the right side is as r f dash c. That means a right hand derivative of the function f of x at the point x is equal to c. Okay, thus f and the function f is differentiable at x is equal to c. I can write the function f of x is differentiable at x is equal to c if and only if L f dash c is equal to r f dash of c. Okay, except this you can't say the function is differentiable at the point x is equal to c. Okay, so if you find that L f dash c is not equal to r f dash r in r of f dash c, then the function will not be differentiable at the point x is equal to c. Now, in the next session, I am showing that if on the last exercise you found that what is continuity. The continuity means a curve which can be drawn in freehand, and there will be no hole or no gap in the curve, so that the function is continuous at a given point, say x is equal to c. But what happens? There may be a question. What do we mean when we say that the function f of x is differentiable at the point x is equal to c? So we want to discuss this one. This is very important concept. So again, we consider the function f of x defined in an open interval. Fx is defined in some open interval, say a comma b. Okay, and I want to draw a curve. Without drawing this one, you can't understand. Say this is the domain line. Say this is y is equal to f of x. This is the curve, and consider that there is a point here. Say this point is p. Okay, and there is a point x is equal to c in its domain. Okay, so with respect to this domain point, the point P on this curve is nothing but your c comma f of c. You know this one, because any coordinate on a curve or in Cartesian plane will be x comma y, like this. X is equal to c here, and f of c means y is equal to f of x. So if you substitute these x by c, then you will get f of c. So the point is c comma f of c. Okay, we consider another 2 points. Say this point is r, and another point is say q. Okay, these 2 points are the neighboring point of the point P. Okay, so let us consider that this point be c plus h comma f of c plus h, isn't it? So there is a short gap from P to R or P to Q. So this point Q will be like this: c minus h comma f of c minus h. Okay, 2 neighboring points R and Q are taken of the point P. So if you join these 2 points, okay, I want to join these 2 points PQ and another 2 points R and P. Okay, so that you are getting 2 chords actually. 2 chords are found. Okay, PQ and RQ. Now you have to see carefully that what is the slope of the chord PQ. The slope of the chord PQ is equal to, PQ is this one. Okay, the chord PQ, and what will be the slope of this one? You know, if 2 coordinates are given, then the slope is y2 minus y1 divided by x2 minus x1, isn't it? So its slope will be f of c okay, you just reverse this one, f of c minus, that will be better, f of c minus h minus f of c upon c minus h minus c, and you may cancel these to c. Again I repeat, we want to find the slope of the chord PQ. Okay, this is your line PQ. So x2 minus x1 divided by y2 minus y1 divided by x2 minus x1. So here f of c minus h minus f of c upon c minus h minus c. So you cancel these two c's, and you are getting now f of c minus h minus f of c upon minus h. Okay, minus h. And what is the slope of the chord, another chord? This is PR. Okay, and again in the same way, y2 minus y1 divided by x2 minus x1. So f of c plus h, write it here, f of c plus h minus f of c upon c plus h minus c. So you may cancel these two c's, and getting here f of c plus f of c plus h minus f of c upon only h. Okay, now we want to use the limits here. Now I change the ink color. Okay, limit h tends to 0 of f of c minus h minus f of c upon h. Okay, I am taking the limiting case when h tends to 0 minus h. When h tends to 0 of f of c minus h minus f of c upon minus h, that means you are taking limit h tends to 0. H tends to 0. What is on left? The slope of chord PQ. So write the slope of chord PQ. Okay, now when h tends to 0, what will happen? When h tends to 0, then you observe that the point q is tending to p, isn't it? Q is tending to p. In this case, the limiting case actually going to like this: limit q tends to p, and it is the slope of the chord PQ. The slope of the chord PQ. Okay, so on the other hand, if you take the other slope, that is a limit h tends to 0 of f of c plus h, very important and interesting also, minus f of c upon h. What happens? It is nothing but the limit h tends to 0, and what is written on LHS? The slope of the chord PR. So write the slope of chord PR. Okay, when h tends to 0 in this chord PR, the point R is tending to P. The point R is tending to P. So you can write a limit R tends to P, slope of the chord PR. Now in both the cases, you see that the point Q and the point R both are tending to P. This is the original point, and these two chords will merge on this P and make a common chord here, unique chord at this point P, and this is actually a tangent, common tangent to both the neighbors. Okay, because both the neighboring points R and Q and their respective chords are merging on this given tangent. Okay, so now what can we conclude? That fx is differentiable at the point P if and only if there exists a unique tangent at P. In other words, you can say that f of x is differentiable at a point P if and only if the curve does not have P as a corner point. You can't consider at this point a corner point. Why don't we consider at this point a corner? We are discussing in the next. Okay, take this theorem. This is an interesting and very beautiful theorem. If a function is differentiable at a point it is necessarily continuous at that point, but the converse is not always true. Okay, we discussed this one. Let us consider that. Okay, let f of x be differentiable at x is equal to c. Okay, then what does it indicate? It indicates that the limit extends to c f of x minus f of c upon x minus c is equal to f dash c. This exists finitely, isn't it? Because it is given. If a function is differentiable at a point, we consider the point is x is equal to c. That means f dash c is equal to limit extends to c f of x minus f of c upon x minus c. This exists finitely. Now, since it is given the function is differentiable, now what to show? You have to show that the function is continuous. That means this is sufficient to show that a limit, just show, to prove it continuous, just show a limit extends to c of the function f of x is equal to f of c. So take its LHS. Okay, so take the LHS. Your LHS is now limit extends to c of the function f of x. Okay, now can you write it as limit extends to c f of x minus f of c? You just introduce this one, minus f of c plus f of c, such that the resultant is same. Okay, next, limit extends to c f of x minus f of c. You divide this one by x minus c and again multiply by x minus c. Okay, plus f of c as usual. Nothing is changed, just you have divided by x minus c, then you multiplied this fraction by x minus c, so that x minus c is cancelled. The resultant is as usual of the previous one. So now you separately use the limits x tends to c f of x minus f of c upon x minus c into a limit extends to c of x minus c. Okay, plus a limit extends to c of f of c. Now carefully watch, there are two terms, this is separation used plus, and limit extends to c x minus c is equal to 0. That means this part is equal to 0, total is 0, so only remaining part is limit extends to c of f of c. So you can write now only limit extends to c of f of c, and you see that this is nothing but your f of c. Okay, this is f of c, and this is your RHS. You see, you try to show that limit extends to c f of x is equal to f of c. So we have found limit extends to c of f of x is equal to f of c. So you can say that therefore f of x is continuous at x is equal to c. The function is continuous at x is equal to c. So the first part is proved, but the converse is not always true. The converse is not always true. For this, I want to take an example. What is the converse? Converse means if a function is continuous, that it does not indicate that it is always different. The function will be always differentiable at a given point. Okay, I want to take an example. Let us consider that for the reverse one. Let us consider that f of x is equal to say modulus of x. Okay, this is the modulus function taken. Okay, you know the modulus function, the curve of these, there will be two parts, piecewise function actually. Okay, you know, at the point x is equal to 0, the function is always continuous because its RHL, right hand limit, left hand limit, and the value of the function at the point x is equal to 0 are all 0. Isn't it? Again I write LHL is equal to RHL is equal to f of 0, and they are all equal to 0. For this, the function is continuous at the point x is equal to 0, isn't it? The function is obviously continuous at this point, at the origin. But can you say the function is differentiable at the point x is equal to 0? For this, you have to show mathematically or by graphically also. I will show it graphically later. Before that, you show mathematically. Fx is modulus of x. Okay, what will be r of f dash 0? That means right hand derivative at x is equal to 0 is equal to limit. Use the definition, limit h tends to 0, not x tends to 0. Limit h tends to 0. What is definition? F of 0 plus h minus f of 0 upon h. This is the definition I used here. Now this is equal to limit h tends to 0. Okay, f of 0 plus h, obviously this is f of h. And what is f of h? F of h means modulus of h minus f of 0. What will be f of 0? F of 0 is 0 mod 0. That means again 0 upon h. Mod h, you know, this is equal to h. H divided by h is equal to 1. So limit is 1. Okay, take the RHL. Take the this is right hand derivative. Now take left hand derivative. That means LF dash 0. LF dash 0 is equal to limit h tends to 0. H tends to 0. F of 0 minus h, 0 minus h minus f of 0 upon minus of h. Now limit h tends to 0. Limit h tends to 0. Numerator f of minus h. F of minus h means modulus of minus h, right? Modulus of minus h minus f of 0. Obviously my f of 0 is equal to 0 because modulus of 0 means 0 upon minus h. Now what is modulus of minus h? Modulus of minus h is equal to plus h. So plus h divided by minus h is equal to minus 1. So this is minus 1. Now observe carefully. This is minus 1 and this one is plus 1. That means RHD is plus 1. RHD, right hand derivative at x is equal to 0 is plus 1, and LHD, this is LHD, a left hand derivative at x is equal to 0 is minus 1. So since LHD and RHD are not equal, so the function is not differentiable at the point x is equal to 0 at the origin, isn't it? So on the other hand, you can also consider since the point is x is equal to 0, you are finding whether the function is continuous or differentiable at the point x is equal to 0. You observe that the neighboring tangents at the point x is equal to 0 will be this line, actually this line and that line. What is this line? This is equal to y is equal to plus x, and this one is y is equal to minus x, isn't it? Now you consider that y is equal to mx plus c. So what is the slope of this line? The slope of this line is equal to minus 1. The slope is equal to minus 1. And what is the slope of this line? Y is equal to x. The slope is plus 1. Y is equal to mx plus c. M is equal to 1. That means slope of this line is equal to 1. So slope is nothing but your derivative at the point x is equal to 0 at the given point. Now this point is x is equal to 0. Since the left hand derivative is minus 1 and right hand derivative is equal to plus 1, so no one of them equal to each other. So for this, the function is not differentiable at the point x is equal to 0. Moreover, the function was continuous at the given point x is equal to 0. Okay, so the function is differentiable at the point, it is necessarily continuous at that point, but the converse is not always true. Okay, next. We have taken a question from NCERT book, so keep watching. Show that the function f of x is equal to x minus 1 if x is less than 2, and twice x minus 3 if x is greater than or equal to 2 is not differentiable at the point x is equal to, not differentiable at the point x is equal to. Okay, we take RHD. Okay, first of all, RHD is equal to, that means r of f dash 2. R of f dash 2 is equal to limit, use the definition, limit h tends to 0, f of 2 plus h minus f of 2 upon 2 plus h minus 2, that is 2 cancel, so divided by 2 h. And what is it? Limit h tends to 0. You carefully watch because I am now applying the formula. F of 2 plus h, that means x is more than 2. f of 2 plus h. That means x is more than 2. Now here see that the domain x is more than 2. The function is 2x minus 3. The function is 2x minus 3. So 2 times x is replaced by 2 plus h. 2 plus h minus 3. Next, minus f of 2. What is f of 2? F of 2, x is equal to, at the, that means the value of the function f of x at the point x is equal to 2. That will be 2 into 2 minus 3. 2 into 2 is equal to 4. 4 minus 3 is equal to 1. So, minus 1. 2 to the 4 minus 3 means 1. So, minus 1 whole divided by h. Now, this is equal to limit h tends to 0 and 2 to the 4, right, 4 plus 2h minus 4 is cancelled upon h. Now h can be cancelled because h tends to 0, h is not is equal to 0. Okay, right. Limit h tends to 0, twice h divided by h. You can cancel these two h's because you have to write the reason. Since h tends to 0, therefore h is not is equal to 0. That means the denominator is not 0. You can cancel these two h's. So getting 2. That means RHD is equal to 2. Now find the LHD. Okay, what is your LHD? LHD, left hand derivative. The left hand derivative, use the definition limit h tends to 0. Okay, f of 2 minus h minus f of 2 upon h minus h. This is the definition. So limit h tends to 0, watch carefully the numerator, f of 2 minus h, x is less than 2 minus h, x is less than 2, yes, this one, x is less than 2, then the function is x minus 1. So replace this x by 2 minus h, so x minus 1 means 2 minus h minus 1, x minus 1, minus f of 2, as earlier I found 2 into 2 minus 3, 2 into 2 means 4, 4 minus 3 is equal to 1, so substitute here 1 and denominator minus h. Limit h tends to 0 and this is 2 minus 2, that is 0. Okay, if you want to write, then you can write 2 is cancelled, divided by minus h divided by minus h, that is equal to 1. So limit h tends to 0 of 1 is equal to 1. So you are getting RHD means your, what is RHD? RHD means this is LHD. LHD means L of f dash 2. L of f dash 2. This is equal to 1. Now watch carefully. Your LHD and RHD are not equal. Since the LHD and LHD is not is equal to RHD at the point x is equal to 2. Therefore, f of x is not differentiable, at x is equal to 2. Okay, so students, I have discussed everything and one question is also solved. Now you have to go through the theory parts of the NCERT book carefully and read carefully, and you will find many problems and you may solve these problems, and if you can't solve, then obviously you may call me and I shall solve everything if I can. Now this is the time to practice at your home. You practice all the questions whatever given in your examples and in the exercise of your NCERT book, also R.D. Sharma, and after that if any problem persists, solve. Okay, till then, bye bye, have a nice day.